Hello everyone, it is a great pleasure and honor to participate in this IMARC Circularity section. My apologies for not being able to join you in person this time. I would really like to thank the organizers for allowing me to submit this video. My name is Fernández-Iglesias. I am a chemical engineer specialized in environment, and I also have a PhD in mining waste management. I've been working for over 16 years now in research and development, always focused on circular economy, sustainable mining, and industrial innovation. For those of you not familiar with ArcelorMittal, we are leader in all major global steel markets and with a very strong R&D internal structure. We are a major producer of steel in many regions, and we have a growing presence in Asia. We are also one of the world's largest producers of iron ore, and we are strategically positioned to serve both our network of steel plants, but also the external global market. And I could be using many company slides to talk about the amazing properties of steel and how it is a material that it's shaping the world as we know it and surrounding all of us right now. But I'm going to recommend this great book, Material World, from Ed Conway, that explains it very well. In this book, Ed Conway explains that not everything in the world is obviously made of steel, but nearly everything in the world is made with machines made of steel. So if you think of other amazing materials surrounding us, like it can be wood, any type of plastic, or concrete and cement, they are not steel, but all the processes to get them is using machines or equipments made of steel. To talk a little bit more about my company, our iron ore production last year was 42 million tons, with more than half of it from North America in our Canadian operations. We also have a presence, as you can see, in South America, Europe, Africa, and other regions like Asia. And our self-sufficiency with our mining operations last year reached 74%. Here you can see two pictures from our two main sites that serve the global market, not only our steel plants, which are ArcelorMittal Mines Canada and Liberia. They are both going through an expansion to reach the high qualities required for decarbonized steels. And our footprint, as you can see, it's quite widespread, with presence in Canada, Mexico, Brazil, Liberia, Europe, Ukraine, and also India, in some cases through joint ventures. And these two images try to convey all the complexity of mining circularity. I will explain myself. Decarbonizing steel demands higher quality ores. So in order to get to the decarbonized world that we need to reach, we need to convert those rocks on the left on high quality iron ore on the right. So all that variability from Mother Earth, which is represented in this slide just by that simple arrow, is all the complexity from our geological bodies that go to the tailings. In this slide, which is a jar that I have in my office and also at the entrance of our lab in Spain, I show how this variability is a reality. So for us, there is not such thing as a single iron ore tailing. All what you can see there is different tailings streams from different sites that we have in our company. That means that this complexity is not only during the lifetime of the mine or when we make changes in our mineral processing scheme, but also site to site. So this has huge implications when it comes to researching, understanding what we have, and also applying circularity and industrial symbiosis. And before I go in more detail what we do with our tailings, I would like to explain some basic data about our global research and development structure. We have a vast network of researchers, 1,700 right now. Last year, we invested $300 million in our R&D programs, and we are located, those labs are located in different geographical sites worldwide. So that means that we have broad mix of nationalities, different generations as well, and trying to work together in result-driven projects. So I have tried to simplify in 3 axes the way we are reimagining our tailings in ArcelorMittal R&D. In a very simplified way, we try to switch from risk to robustness, from residues to resources, and going one step further from liabilities to legacies. Let's start on how we try to switch from risk to robustness. I know that this is not the focus of this session, but I think it's very important to understand the links with circularity. Let me start with the way we are evolving what we measure and how we measure it. A simplified formula could be developing the technologies ourselves or scouting the technologies being developed by others, adapting them to our specific needs, and then adopting them once we have proven its value on a real site. So we do that with all types of technologies, from ground monitoring to satellite, drones, imaging, or any kind of sensor that can provide any valuable information about our tailings and tailings storage facilities. So I have highlighted here just 3 examples of consortium projects where we have participated, and we do, like you can see in the picture on the right-hand side, real proof of concept under real conditions in one of our sites, in this case in Bosnia. So it's obviously very important to understand what we have in our tailings and what we will have in our tailings storage facilities in 3, 5, or 10 years' time. This is not so much related to circularity, it's true, but I wanted to highlight this case because we are also trying to go one step further, predicting the behavior of tailings. We are partnering with top researchers worldwide, in fact with the University of South Wales in Sydney, to prevent tailings dam failures. We are also working with other universities or other relevant laboratories that have expertise on this to tackle this challenging problem. One very important role of research and development in our company is technically supporting our mining operations. So we have very strong capabilities for the watering, transport, and disposal of our tailings streams. We have tailings management labs in Spain, where we receive samples from tailings all over the world. And we have full synergy with other mineral processing labs that we have in France that are responsible to design and optimize our beneficiation processes. So obviously these 2 laboratories work together hand in hand to understand how mineral processing affects the tailings. We also work together with our mining teams in each site, with CTO, with PMO, and even with engineering companies and other key stakeholders. And over the years, I have found that this is a very important part of R&D because it's key to access mine info and reliable data. Some other breakthrough research we do to increase robustness could be, for example, researching on cementing additives with a goal to be able to do a future disposal in a rock-like state. A good example that we published in a congress this year is about the use of fibers to try to increase the stability of our tailings deposits. So you can see we have used, in this case I just highlighted 3 of them, but we tested different types of fibers, we mixed them with our tailings, and then we did all the geotechnical assessments to understand how they could improve the stability of tailings. And now let's go how we are trying to switch our concept of tailings from residue to resource. Here we can see an example of something we have published recently. It's true that we do not publish much of the research we do internally, but here is one case of evaluation of a new mineral processing scheme to recover the iron from a fine tailings stream. So obviously, some of our tailings streams still contain very important concentrations of iron ore. So mineral processing technologies and equipment continue evolving, and the tailings of today will be the mines of the future. And linked to the monitoring that I commented before, understanding, characterizing, and monitoring our tailings composition is key. That is why we also have a geometallurgy R&D program that plays a very important role in predicting all our outputs, not only the ore production, but the tailings production. Okay, so what about mining circularity? Let's focus on our product, okay? Steel. Think about your car. It probably uses around 1 ton of steel. To understand circularity, we really need to see the big picture. So to produce that 1 ton of steel that goes in your car, we also produce 0.4 tons of slags and 0.1 tons of sludge and dust. Those are the total outputs of the 1.5 tons that go through the blast furnace and the subsequent processes in steelmaking. And the truth is that not only steel is a highly recyclable material, but the process itself is quite circular as well. So you can see in this graph from World Steel how the steel production output really only has a 3% more or less of waste. 65% could be the steel material, but then 33% are what we call steel byproducts, such as slag or dust. So in those cases, we have already done our homework and we have researched applications and industrial symbiosis relationship with other sectors, such as cement, asphalt, roadstone, or in the case of the dust, where we have high contents of iron and zinc, we recycle it internally. We also in the process recycle many of the process gases, and we have other minor byproducts. And the truth is that this circularity in the steel process is supporting the carbonization of the economy. Because, for example, in 2023, cement industry reused 9 million tons of our slags, avoiding 7 million tons of CO2. And the truth is that if you go to a steel plant, probably they will consider that upstream is what we see on the left side on this slide right now. But we in mining know that the real upstream goes beyond that. So to be able to process that 1.5 tons of iron ore concentrate in the steel making process, we've really had to process 3.8 tons of material. So the result is that for each ton of steel, we really generate an average of 2.3 tons of tailings. Of course, this is an average made with different cases that we have because we have different production sites and the ratios can change, but this could be an average of iron ore production. The full picture gets completed with the waste rock that could be an average of 3.5 tons per ton of steel. So obviously tailings have most of our focus because of their complexity, because of the costs of managing them, the inherent risk that the tailings storage facility can have. But we should not forget that waste rock is also a source of material and could be used in future industrial symbiosis schemes. So to summarize the big picture, obviously circularity in our mining operations with the focus on reusing and recycling materials beyond just the iron ore is a top priority in our R&D portfolio strategy. From all the different industries that we are exploring to use our tailings, it's true that construction is one of the key ones because of the higher volumes of consumption that it can have. So depending on our tailings compositions, remember the picture that I showed at the beginning, they are totally different one from the other. So we have to explore one by one. So we are exploring different applications, for example, as a substitute of cement in the clinker production or as a source of fine and coarse sand, depending on the tailing, or even aggregate in concrete. But also depending on the compositions and the clay's content, we are also exploring with different industries the ceramic market. So roof tiles or floor tiles or even wall tiles. A simplified way to explain how we are doing this is maybe explaining our R&D strategy. So basically we start gathering all the information from our internal tailings. That is, understanding their composition, understanding their physical properties, size by size, And then in parallel, finding out potential applications, okay? What markets, according to the compositions and the physical properties that we have, could benefit from our tailings in each site. So once we detect an opportunity and we do a match, what I ask the researchers is to define, okay, which partners do we want to go with? Because one of the things we want to do is work with those industries. Makes no sense that we internalize all that R&D test work when we can partner with those industries and understand in a fast way if our tailings are feasible for them or not. Once we have a clear overview of the resources and the scope that we need, is a go, no go. Once we have passed that gate, the project leader should start a technical feasibility, in most cases at a lab scale. In parallel with that, we perform a preliminary market analysis and some IP study to understand if we need any patent or similar. So obviously, circularity is very regional, and logistics can kill many of the business cases we have. That is why it is very important to understand if we have a local or regional market for that application. Once that we passed that lab scale technical feasibility, there is another go, no go, and we decide if we go for an industrial scale proof of concept. And finally, I would like to highlight a project that is inspired also in circularity, but with a different focus, trying to switch from a liability to a legacy. This year, we have just started a pioneering R&D project in Brazil, where what we aim is to regenerate soils through circularity. We have different mines in Brazil, Andrade and Serra Sul, and we also have a bioforest, which is a eucalyptus plantation for creating our own biochar that feeds the steelworks. So this is a 3-year project led by our R&D Brazil unit, and it's technically supported by the Universidad Federal do Viçosa in Minas Gerais. The goal here is to use organic waste from the mining operations, the tailings and waste rock, and aiming to create a fertile soil that is capable of supporting local biodiversity for degraded areas. So obviously the goal is not only to use it in our internal sites, in our mines, for recovering or closure of some tailings dam, but also donate it to the community if it's needed in some cases for degraded areas. With this, I finish my presentation. I hope it has been useful to understand how we are changing the way we understand circularity in the full metals and mining value chain. Thank you for your attention, and thank you again, IMARC, for allowing me to submit this video. Have a great rest of the Congress.